What if the world you live in, roads, bridges, tunnels, cities, was built by decisions you haven't even learned yet? Welcome to Civil Engineering Edge, the place where engineering meets reality. This is not just about concrete and steel. This is about how ideas become structures, how calculations shape skylines, and how engineers solve problems where failure is not an option. From underwater tunnels and offshore giants to smart cities, sustainable materials, and future-ready infrastructure here, we break down complex engineering concepts into clear, practical knowledge. Whether you're a student building your foundation, a professional sharpening your edge, or a curious mind fascinated by how the world is built to belong here, this channel is about thinking like an engineer, designing with purpose, and understanding the science behind every structure that stands strong against time and nature. You're not just watching a video, you're stepping into the engineering mindset. Welcome to Civil Engineering Edge, where tomorrow's infrastructure begins today. Imagine building a bridge, but entirely underwater. No dry land, no stable ground, just crushing water pressure, unpredictable currents, and zero visibility. How do engineers pour concrete that doesn't wash away? How do they weld steel where humans can barely survive? And how do they stabilize structures that weigh more than skyscrapers on soft seabeds hundreds of feet below the surface? Welcome to the astonishing world of underwater construction, where engineers don't just fight gravity, they fight the ocean itself. From submerged tunnels beneath busy shipping lanes to massive offshore foundations standing strong against waves and corrosion, this is a realm where precision, material science, and engineering courage collide. Today, we're diving deep into the secrets that make the impossible possible. Diving into the deep. Why underwater construction? Underwater construction exists because the modern world refuses to stop at coastlines. As cities grow denser and transportation demands increase, engineers are forced to look beneath rivers, seas, and oceans to create faster, safer, and more efficient connections. Unlike traditional construction, underwater projects are not optional luxuries. They are engineering necessities driven by geography, population pressure, and global trade. Surface-level solutions such as bridges are not always feasible. Busy shipping lanes require unobstructed navigation. Deep waters make bridge foundations impractical, and environmental constraints limit above-water structures. In these situations, underwater tunnels and submerged foundations become the only viable solution. These projects allow uninterrupted transport while preserving the surface environment. But underwater construction is more than problem solving. It represents the evolution of civil engineering. It pushes boundaries in geotechnical engineering, structural design, marine construction methods, and material science. Every underwater project must address complex challenges such as hydrostatic pressure, buoyancy forces, seabed instability, corrosion, and long-term durability. What makes underwater construction remarkable is not just the final structure, but the process itself. Engineers must design systems that can be built remotely, monitored digitally, and maintained for decades in hostile environments. Each project becomes a laboratory of innovation, where mistakes are costly and precision is non-negotiable. In essence, underwater construction exists because modern civilization demands connection without compromise, even when nature places the most extreme obstacles in the way. Beyond bridges, the hidden world beneath the waves demanding new infrastructure. When most people think of infrastructure, they imagine roads, bridges, and skyscrapers. But beneath the water as surface lies a hidden world of critical infrastructure that keeps modern society functioning. This submerged realm includes transportation tunnels, offshore energy platforms, underwater pipelines, communication cables, and marine research facility systems that operate silently yet powerfully below the waves. Traditional bridges often dominate visual landscapes, but they come with limitations. In deep or wide water bodies, bridge spans become extremely expensive, vulnerable to ship collisions, and exposed to harsh weather conditions. Underwater tunnels eliminate these risks by passing below navigation channels, allowing uninterrupted maritime traffic while providing safer, more resilient transport routes. Beyond transportation, underwater infrastructure supports global energy needs. Offshore wind turbines, oil and gas platforms, and subsea pipelines rely heavily on underwater construction techniques. These structures must anchor securely to seabeds that may consist of soft clay, sand, or fractured rock, each demanding specialized foundation solutions. The ocean floor is also home to vital communication networks. Submarine cables carry over 95% of global internet traffic, requiring precise installation and protection against currents, seismic activity, and human interference. What makes this underwater world extraordinary is that engineers rarely get second chances. Visibility is limited, access is difficult, and repairs are expensive. Every design decision must account for decades of service life under constant exposure to salt water, pressure, and biological activity. Underwater construction isn't just about building below water, it's about creating invisible lifelines that support economies, security, and daily life across the planet. Economic and strategic imperatives driving these ambitious projects. Underwater construction is not driven by curiosity alone, it is powered by economic necessity and strategic planning. In an interconnected global economy, delays in transportation, energy supply, or data transmission translate directly into financial losses. Submerged tunnels and offshore structures often provide the most efficient and long-term solutions. From an economic perspective, underwater tunnels significantly reduce travel time between major urban centers, increasing productivity and regional integration. Cities separated by rivers or seas can function as a single economic zone when connected below water. This improves logistics, boosts tourism, and raises property values on both sides of the crossing. Strategically, underwater infrastructure enhances national security and resilience. Subsea tunnels are less vulnerable to extreme weather, terrorism, or surface-level accidents compared to bridges. Military logistics, emergency evacuations, and essential supply routes benefit from protected underwater corridors. Energy security is another major driver. Offshore oil, gas, and renewable energy installations require robust underwater foundations and pipelines to deliver power reliably. Countries investing in offshore wind farms depend heavily on underwater construction to meet sustainability goals and reduce carbon emissions. There is also a geopolitical dimension. Nations compete to control trade routes, seabed resources, and communication networks. Advanced underwater construction capability reflects technological leadership and engineering strength. Although these projects demand enormous upfront investment, their long-term economic returns often outweigh costs. When designed correctly, underwater structures can serve reliably for 100 years or more, making them strategic assets rather than expenses. The sheer scale and engineering audacity required to build underwater. Building underwater is not just difficult, it is audacious. Engineers must plan projects where gravity, buoyancy, pressure, and corrosion all work against them simultaneously. Unlike surface construction, where adjustments can be made easily, underwater construction demands near-perfect execution from the very beginning. Consider the scale alone. Immersed tunnel elements can weigh tens of thousands of tons, yet they must be floated, positioned with centimeter-level accuracy, and sunk into prepared trenches on the seabed. All this happens while accounting for tides, currents, and weather windows that may last only a few hours. Hydrostatic pressure increases dramatically with depth, placing extreme stress on structures and construction equipment. At the same time, buoyant forces try to lift massive components upward, requiring precise ballast control. Engineers must design systems that remain stable during construction and for decades afterward. Human access is limited. So much of the work relies on remotely operated vehicles, divers trained for high-risk environments, and advanced monitoring systems. Every weld, joint, and seal must perform flawlessly because underwater repairs are complex and expensive. What truly defines underwater construction is the engineering mindset, a willingness to operate where failure is not an option. These projects combine structural engineering, geotechnical analysis, fluid mechanics, material science, and project management at the highest level. In short, underwater construction is where civil engineering proves its boldest claim. If it can be imagined, it can be built even beneath the ocean floor. The blueprint for submerged passages, tunneling techniques. When engineers decide to build a tunnel underwater, the first and most critical question is how. Unlike land tunnels, underwater tunnels must resist hydrostatic pressure, prevent leakage, and remain stable on or beneath soft seabeds. The selected tunneling technique becomes the backbone of the entire project, influencing cost, construction time, safety, and long-term durability. Underwater tunneling techniques are broadly categorized based on geology, water depth, environmental conditions, and navigation requirements above. Shallow water crossings often favor construction on the seabed itself, while deeper or rockier conditions demand excavation through the ground below. Each method comes with its own engineering philosophy and risk profile. Precision planning begins long before construction starts. Engineers conduct extensive bathymetric surveys, geotechnical investigations, seismic studies, and hydraulic modeling. These studies determine soil strength, rock quality, groundwater pressure, and potential settlement risks. Even minor miscalculations can lead to leakage, structural distress, or catastrophic failure. Unlike bridges, where visibility allows continuous inspection, underwater tunnels must be designed as sealed systems capable of resisting water ingress for decades. Structural linings, waterproof membranes, and joint systems must work perfectly together. Modern submerged tunnels represent a fusion of structural engineering, marine construction, and advanced machinery. From floating massive concrete sections into position to boring deep beneath riverbeds with tunnel boring machines, underwater tunneling showcases the peak of civil engineering coordination. At its core, underwater tunneling is not just about excavation, it is about mastering the environment where water dominates every design decision. Immersed tube method. Prefabricated sections sunk and joined. The immersed tube method is one of the most iconic and visually fascinating techniques in underwater tunnel construction. Instead of digging entirely underground, engineers build massive tunnel sections called elements on land in controlled casting yards. These reinforced concrete or steel elements are typically 100 to 150 meters long and weigh thousands of tons. Once completed, each element is sealed at both ends and floated like a ship to the tunnel site. A carefully dredged trench is prepared on the seabed, often lined with gravel or bedding material for uniform support. Using GPS positioning, ballast tanks, and tugboats, engineers slowly sink the tunnel element into the trench with millimeter-level accuracy. This method has been widely adopted in Asia for large-scale projects such as underwater metro systems and sea crossings, where shallow water depths and soft marine soils are common. The controlled prefabrication ensures superior concrete quality, better waterproofing, and faster installation compared to in situ construction. One of the biggest advantages of the immersed tube method is reduced disruption to surface navigation. Shipping traffic can continue above while tunnel elements are placed below. Additionally, construction time is significantly shorter once installation begins. However, the method demands extreme precision. Any misalignment during placement can compromise joint integrity. Engineers must also account for buoyancy forces, seabed settlement, and seismic activity. The immersed tube method proves that sometimes the smartest way to build underwater is not to dig, but to assemble. Bored tunnels, giant TBMs beneath rivers and seas. When water depths increase or seabed conditions become complex, engineers turn to bored tunnels constructed using tunnel boring machines, or TBMs. These massive machines, sometimes over 15 meters in diameter, excavate tunnels deep beneath riverbeds or seabeds, adapting land-based tunneling technology for underwater challenges. Underwater bored tunnels are typically constructed well below the seabed to avoid direct water pressure and navigation risks. The surrounding soil or rock acts as a natural barrier, but groundwater pressure remains a major concern. To address this, specialized TBMs such as Earth Pressure Balance (EPB) or Slurry Shield TBMs are used. These machines maintain pressure at the tunnel face, preventing water and soil from rushing in. As the TBM advances, it installs precast concrete lining segments immediately behind the cutter head, forming a continuous, watertight tunnel lining. One major advantage of bored tunnels is minimal impact on marine ecosystems and surface activities. Since excavation happens deep underground, shipping lanes, ports, and coastal infrastructure remain unaffected. However, bored tunneling underwater requires extreme control. Variations in soil layers, high pore water pressure, and machine breakdowns can lead to ground settlement or flooding. Continuous monitoring of face pressure, settlement, and alignment is essential. Bored tunnels represent engineering patience and precision. Unlike immersed tubes, progress is slow but highly controlled. They are a testament to how civil engineering adapts traditional methods to conquer one of the most hostile construction environments on Earth. Connecting the sections, watertight seals under immense pressure. The most critical moment in underwater tunnel construction is not excavation, it is connection. Whether using immersed tubes or bored tunnels, creating a perfectly watertight joint under immense water pressure is a true engineering test. In immersed tube tunnels, each prefabricated element is joined underwater using advanced sealing systems. Rubber gaskets often made of synthetic neoprene are compressed between tunnel segments. When the elements are pulled together using hydraulic jacks, the gasket deforms, creating a tight seal capable of withstanding external water pressure. Temporary bulkheads are removed only after the joint is confirmed watertight. Engineers monitor leakage, pressure behavior, and alignment before proceeding to the next element. A single faulty joint can compromise the entire tunnel. For bored tunnels, precast lining segments are bolted together with precision. Each segment joint contains multiple sealing layers, including elastomeric gaskets and secondary waterproof membranes. These systems accommodate slight movements caused by temperature changes, settlement, or seismic activity. Water pressure at depth can exceed several bars, meaning even microscopic gaps can lead to long-term seepage. Therefore, joint tolerances are measured in millimeters, and quality control is relentless. Advanced sensors are embedded to monitor joint behavior throughout the tunnel's life. Modern tunnels are not just sealed, they are actively monitored systems. In underwater construction, a tunnel is only as strong as its weakest joint. That SY connecting sections beneath the water isn't just construction, it is engineering precision at its absolute finest. Anchoring giants, building offshore structures. Offshore structures, whether oil platforms, wind turbines, or subsea terminals, face forces unlike any land-based construction. Waves, currents, tides, wind, and seismic activity act simultaneously, while corrosion and fatigue work silently over decades. The greatest challenge is not building upward, but anchoring downward into an unpredictable seabed. Unlike buildings on land, offshore structures cannot rely on shallow foundations. The seabed may consist of soft clay, loose sand, or fractured rock, each behaving differently under load. Engineers must design foundations that resist vertical loads, lateral wave forces, uplift due to buoyancy, and cyclic fatigue caused by continuous wave action. Foundation choice depends on water depth, soil conditions, environmental loads, and construction feasibility. Shallow waters with strong seabeds favor massive gravity-based systems, while deeper waters or weaker soils demand pile-supported foundations. Each solution requires precise geotechnical analysis and extensive physical modeling. Offshore foundations are typically constructed under tight weather windows. A small miscalculation in timing or positioning can delay projects by months. Once installed, these foundations must perform with minimal maintenance, often for 30 to 100 years. What makes offshore foundation engineering remarkable is its scale. Individual foundation units can weigh more than skyscrapers, yet must be placed with centimeter-level accuracy on the ocean floor. In offshore construction, foundations are not just supports, they are the difference between structural stability and total failure. Gravity-based foundations, massive concrete cases. Gravity-based foundations, or GBFs, rely on one powerful principal weight. These foundations are enormous concrete structures, known as caissons, designed to resist environmental forces simply by their massive self-weight. Once placed on the seabed, gravity alone keeps them firmly anchored. GBFs are typically constructed in dry docks or coastal fabrication yards. High-strength reinforced concrete is used to form hollow caissons, which are then floated to the offshore site. After precise positioning, the caissons are slowly lowered onto the seabed. Once in place, the hollow chambers are filled with ballast materials such as sand, gravel, or seawater. This added mass increases stability, allowing the structure to resist wave action, sliding, overturning, and uplift forces caused by buoyancy. Gravity-based foundations are commonly used for offshore oil platforms and wind turbines in shallow to moderate water depths. They perform exceptionally well on firm seabeds and offer excellent resistance to fatigue loads. One major advantage of GBFs is durability. Concrete performs well in marine environments when properly designed, offering high resistance to corrosion compared to steel. Maintenance requirements are relatively low over the structure's life. However, GBFs require extensive seabed preparation. The seabed must be leveled and strengthened to avoid differential settlement. Transporting and installing such massive structures also demands specialized vessels and calm weather conditions. Gravity-based foundations demonstrate how engineering sometimes chooses brute force executed with precision to conquer the ocean. Pile foundations, driving colossal piles into the seabed. When gravity alone isn't enough, engineers turn to pile foundations, one of the most versatile and reliable offshore anchoring systems. These foundations use long, slender piles driven deep into the seabed to transfer loads to stronger soil or rock layers below. Offshore piles are typically made of steel and can reach diameters of several meters and lengths exceeding 80 meters. They are installed using hydraulic hammers or vibratory drivers mounted on floating platforms or jack-up rigs. Each pile must be driven with extreme accuracy to achieve the required penetration depth and alignment. Pile foundations excel in challenging ground conditions such as soft clay, layered soils, or deep water. They resist vertical loads, lateral wave forces, and cyclic fatigue caused by repeated wave action. Groups of piles are often used to distribute loads and enhance stability. A key engineering challenge is predicting pile behavior under dynamic marine loads. Engineers rely on advanced soil modeling, pile load testing, and real-time monitoring during installation to ensure performance. Pile foundations are widely used for offshore wind turbines, bridges, and deep water platforms. Their modular nature allows flexibility in design and easier adaptation to varying seabed conditions. However, pile driving generates noise and vibrations, which can impact marine life. Modern projects incorporate noise mitigation techniques such as bubble curtains and controlled hammering. Pile foundations showcase engineering adaptability going deep when surface stability cannot be trusted. The evolution of materials, from steel to self-healing concrete. Materials are the silent heroes of underwater construction. Early offshore structures relied heavily on conventional steel and concrete, but harsh marine environments quickly exposed their limitations. Today, materials science plays a critical role in ensuring long-term durability and safety. Steel remains widely used due to its high strength and flexibility, especially in pile foundations and jacket structures. However, corrosion caused by salt water is a constant threat. Protective coatings, cathodic protection systems, and corrosion-resistant alloys are now standard design elements. Concrete has evolved dramatically for marine use. Modern underwater concrete includes low permeability mixes, supplementary cementitious materials, and chemical admixtures that improve durability. Self-compacting concrete allows placement underwater without segregation, ensuring uniform strength. One of the most exciting advancements is self-healing concrete. Embedded microcapsules for bacteria activate when cracks form, producing minerals that seal the cracks automatically. This significantly extends service life and reduces maintenance needs. Advanced composites, such as fiber-reinforced polymers (FRP), are increasingly used for strengthening and corrosion protection. These materials are lightweight, highly durable, and resistant to marine degradation. The evolution of materials has transformed underwater construction from a constant maintenance battle into a long-term durability strategy. In the ocean, where repairs are costly and difficult, smart materials are not a luxury, they are a necessity. Battling the deep, overcoming immense pressures and corrosive environments. Underwater construction is not simply about building below water, it is about surviving the deep. Unlike land-based structures, underwater systems face constant physical and chemical attacks from their environment. Pressure, corrosion, waves, and seismic forces act continuously, not occasionally. At increasing depths, hydrostatic pressure rises rapidly, placing enormous compressive loads on structural elements. Simultaneously, seawater aggressively corrodes metals, penetrates concrete, and weakens materials over time. Unlike surface structures, underwater installations cannot be easily inspected or repaired, making durability a primary design objective. In addition to static forces, underwater structures must withstand dynamic actions. Waves, tides, and currents generate cyclic loads that cause fatigue. Seismic events introduce sudden ground motions, while scour alters seabed support conditions unexpectedly. To combat these challenges, engineers adopt a multi-layered defense strategy. Structural geometry, material selection, protective systems, and monitoring technologies all work together to ensure long-term stability. Safety factors are higher, redundancy is mandatory, and design life expectations often exceed 50 to 100 years. Every underwater structure represents a balance between resisting nature and adapting to it. Failure to account for even one environmental factor can lead to catastrophic consequences. This battle with the deep defines the discipline of marine and offshore engineering, where survival is not measured in days or years, but in generations of service beneath the sea. Hydrostatic pressure, engineering against crushing forces. Hydrostatic pressure is one of the most unforgiving forces in underwater construction. For every 10 meters of water depth, pressure increases by approximately 1 atmosphere. At significant depths, this translates into forces capable of crushing submarines, let alone conventional structures. Underwater tunnels, foundations, and offshore platforms must be designed to resist this pressure continuously. Unlike transient loads such as wind, hydrostatic pressure acts uniformly and relentlessly on every exposed surface. Even small openings or weak joints can become points of failure. Engineers respond by optimizing structural shapes and thicknesses. Circular and curved sections are preferred because they distribute pressure evenly, minimizing stress concentrations. Tunnel linings, caissons, and offshore shells are designed as pressure-resisting structures rather than load-carrying frames. Material selection is critical. High-strength concrete with low permeability reduces water ingress, while steel components are designed with sufficient thickness to prevent buckling. Waterproof membranes and multi-layer sealing systems add additional protection. Construction stages are equally important. During installation, partially completed structures may experience uneven pressure distribution, requiring temporary supports or controlled flooding to equalize forces. Advanced numerical modeling and physical scale testing help engineers simulate pressure behavior before construction begins. Sensors embedded in structures continue to monitor pressure effects throughout service life. In underwater engineering, pressure is not an occasional threat, it is a constant opponent, demanding precision, foresight, and respect in every design decision. Corrosion's relentless assault, protecting structures from the sea. Seawater is one of the most aggressive environments for construction materials. Salt, oxygen, and moisture combine to create a perfect setting for corrosion, particularly for steel components used in offshore and underwater structures. Left unprotected, corrosion can reduce structural capacity dramatically within a few years. To combat this, engineers employ advanced protective systems. The first line of defense is protective coatings. Modern marine coatings include epoxy, polyurethane, and multi-layer systems designed to resist abrasion, chemical attack, and biological growth. These coatings form a barrier that isolates steel from seawater. The second line of defense is cathodic protection. This technique controls corrosion by making the structure the cathode of an electrochemical cell. Sacrificial anodes made of zinc or aluminum corrode instead of the structure, preserving the steel. In large installations, immersed current systems are used to provide continuous protection. Concrete structures are also vulnerable. Chloride ions penetrate concrete and initiate corrosion of embedded reinforcement. Engineers counter this using low-permeability concrete mixes, corrosion inhibitors, epoxy-coated rebars, and increased concrete cover. Regular inspection is challenging underwater, so systems are designed with redundancy and long-term performance in mind. Sensors and remotely operated vehicles assist in monitoring corrosion activity. Corrosion never sleeps. In underwater construction, protection systems are not optional accessories, they are structural necessities that define service life and safety. Seismic and dynamic wave forces. Designing for the ocean's unpredictable power. The ocean is never still. Waves, currents, and seismic events introduce dynamic forces that make underwater construction especially complex. Unlike static loads, these forces vary in magnitude, direction, and frequency, creating fatigue and instability over time. Wave action generates cyclic lateral loads on offshore structures, leading to vibration and repeated stress reversals. Over decades, this can cause fatigue cracking in steel and micro-cracking in concrete. Engineers must design for millions of load cycles, not just peak forces. Seismic activity adds another layer of complexity. Underwater tunnels and offshore foundations may experience ground shaking, seabed liquefaction, and sudden displacement. In seismic zones, structures must accommodate movement without losing watertight integrity or stability. Design strategies include flexible joints, energy dissipating systems, and ductile structural detailing. Pile foundations are often designed to bend without breaking, while tunnel linings allow controlled deformation. Scour caused by wave-induced currents can remove seabed material around foundations, reducing support. Engineers counter this with rock armoring, mattresses, and continuous seabed monitoring. Advanced hydrodynamic modeling helps predict wave and current behavior, while seismic analysis ensures resilience during earthquakes. In underwater construction, engineers don't try to stop the ocean, they design structures that move safely with it, absorbing energy rather than resisting it blindly. The future of underwater cities, innovation and exploration. Underwater construction is no longer limited to tunnels and offshore platforms. As coastal populations grow, land becomes scarce, and climate change reshapes shorelines, engineers are beginning to imagine a future where entire communities and industries extend beneath the sea. Technological advances are rapidly expanding what is possible underwater. Automation, artificial intelligence, and advanced materials are transforming construction methods that were once slow, risky, and human-dependent. At the same time, environmental awareness is redefining how underwater structures interact with marine ecosystems. Future underwater cities will not be isolated concrete shells, but integrated systems combining transportation, energy generation, habitation, and environmental monitoring. These systems must be resilient, self-sustaining, and adaptable to extreme conditions. Engineering challenges remain immense. Pressure resistance, life support systems, long-term habitability, and maintenance access all demand breakthroughs in design and construction. However, the same challenges once made underwater tunnels seem impossible, and today, they operate successfully worldwide. The future of underwater construction represents a shift from defensive engineering, which resists the ocean, to collaborative engineering, which works with it. What once served only industry and transport may soon support human life itself. As innovation accelerates, the ocean floor may become the next chapter of urban expansion design, not by science fiction, but by civil engineers, robotics and AI, autonomous systems below the surface, robotics and artificial intelligence are redefining underwater construction. Where human divers once performed dangerous, time-limited tasks, autonomous and remotely operated systems now take the lead. These technologies improve safety, accuracy, and efficiency in one of the world's most hostile environments. Remotely operated vehicles, or ROVs, are already standard tools in underwater construction. Equipped with cameras, sensors, and robotic arms, they inspect structures, assist in welding, and monitor joint integrity. Autonomous underwater vehicles, or AUVs, go a step further by navigating independently, mapping seabeds, and detecting defects using AI-driven analysis. Artificial intelligence enhances decision-making. Machine learning algorithms analyzed sensor data to predict corrosion rates, structural fatigue, and maintenance needs long before failures occur. Digital twins, virtual replicas of underwater structures, allow engineers to simulate performance under real-time environmental conditions. Robotic systems are also being developed for underwater concrete placement, precision cutting, and automated inspection. These systems can operate continuously, unaffected by depth, pressure, or human fatigue. In the future, entire construction sequences may be coordinated by AI, optimizing installation timing based on tides, weather, and seabed behavior. Maintenance could shift from reactive repairs to predictive intervention. Robotics and AI are not replacing engineers, they are extending human capability into depths where direct presence is impossible. Sustainable practices, building with the ocean, not against it. Sustainability is becoming a defining principle of underwater construction. Early offshore projects focused solely on structural performance, often disrupting marine ecosystems. Today, engineers are rethinking designs to minimize environmental impact and even enhance marine life. Modern underwater projects begin with extensive environmental impact assessments. These studies guide construction methods that reduce sediment disturbance, noise pollution, and habitat destruction. Techniques such as controlled pile driving, bubble curtains, and precision dredging help protect marine organisms. Materials also play a key role. low-carbon concrete mixes, recycled aggregates, and corrosion-resistant composites reduce environmental footprint while increasing durability. Longer service life means fewer repairs and less intervention in sensitive marine environments. Some underwater structures are now designed as artificial reefs. Textured concrete surfaces encourage coral growth and marine biodiversity, transforming infrastructure into ecological assets. Offshore wind turbine foundations often become thriving marine habitats over time. Energy efficiency is another focus. Underwater facilities increasingly integrate renewable energy sources, such as offshore wind and tidal power, to support operations sustainably. Sustainable underwater construction reflects a philosophical shift. The goal is no longer just to survive the ocean, but to coexist with it responsibly, ensuring infrastructure development does not come at the cost of marine ecosystems. The next frontier: submerged habitats and resource platforms. The idea of fully submerged habitats is moving from science fiction toward engineering reality. Research facilities, underwater hotels, and experimental living modules already exist, offering glimpses of a future where humans may live and work beneath the sea for extended periods. These habitats demand revolutionary design approaches. Structures must withstand pressure while maintaining comfortable internal environments. Life support systems must regulate oxygen, temperature, humidity, and waste with minimal external input. Emergency evacuation and long-term maintenance remain critical challenges. Beyond habitation, underwater construction will support advanced resource extraction platforms. Deep-sea mining, subsea energy storage, and offshore renewable hubs require robust, remotely operated infrastructure. Engineers must balance resource demand with environmental responsibility. Floating submerged hybrid structures may become common, combining surface access with deep water stability. Modular designs will allow expansion, repair, and relocation as needs evolve. These developments will rely heavily on advanced materials, AI-driven monitoring, and robotic construction. Human presence will be minimized, while systems operate autonomously for long periods. The ocean represents Earth's largest unexplored frontier. As land resources diminish and technology advances, underwater construction may redefine how humanity expands. The next great cities may not rise into the sky but descend beneath the waves, engineered by visionaries who dare to build where few have ever lived. Every structure you see around you, every bridge, tunnel, and tower started as an idea on paper. And today, you took one step closer to understanding how those ideas become reality. At Civil Engineering Edge, our mission is simple: to help you learn deeper, think smarter, and engineer better. If this video expanded your understanding, strengthened your concepts, or sparked your curiosity, make sure to like, share, and subscribe. Because the future of infrastructure needs engineers who don't just follow formulas, but understand the why behind them. Drop your questions and thoughts in the comments. We build knowledge together here. And don't forget to turn on notifications, because the next video might just change how you see the world around you. Until then, keep learning, keep building, keep pushing your limits. This is Civil Engineering Edge. Stay sharp, stay engineered.